So far we talked about density estimation, and let's move on to clustering. Speaking of the clustering, we are under the realm of unsupervised learning. So there are multiple categories of the learning technique that we talked about. So the first one, unsupervised learning. The other one, supervised learning. So these two are big two regime. And unsupervised learning, you have set up data, and those data does not have target value. So each data instance only consists of some set of observation. So this is a big assumption. And where the goal is to find out interesting patterns in the data. So what are the interesting patterns? So where maybe you are trying to find out the distribution of your data. So that's what we have done, density estimation. So density estimation indeed one method that falls in the category of unsupervised learning. But the other interesting pattern that you can see from data set that is clusters. So you can understand cluster as the natural distribution of the data, or natural separation or natural grouping of the data. So I used to use this kind of expression: init groups from the data set. So here is another visualization. So density estimation, where you have set of data, and we want to estimate some kind of quantification representing the distribution of the data. Well, they can be understood as drawing some kind of shape like this, again representing the distribution of the data. Clustering is taking another approach towards the data set. So where you have given set of data, and according to some aspects that you can observe, you want to separate them. So where based on the shape and color, where we can easily separate the data in this way. So that is a simple toy example. So where if you consider each of these shapes represented by color and number of points that each polygon has, and you can easily come up with this cluster. Where sometimes clustering method, sometimes that is a perfect cluster, but sometimes where it may have some kind of mixture of different, conceptually different classes. But it's okay. So where what we are doing is trying to roughly separate the data, and that separation may help us to understand the data better. So overall, well, this kind of analysis called as EDA, or exploratory data analysis. So once you have set up data, you first want to get the sense of the data. So with techniques that falls in this EDA, they usually give you better understanding of the data set at your hand. This is what data looks like eventually, where we normally think of tabular data. So data are given in a table form. So again, each row represents a record, and each column represents a variable or observation. So speaking of EDA, so when you first receive the data, what would you like to do first? So this is the question that you can draw, and the answer could be one of the techniques from EDA. So maybe you can apply some simple statistics like average, standard deviation, median, minimum and maximum. Well, that will give you the sense of the data. So speaking of getting transcription from a set of students, maybe you can get the minimum score and maximum score from the last exam. Then you can sort of draw some rough diagram in your brain where this is the average understanding that each student has, something like that. In many cases, the kind of simple statistics work, but sometimes you have data in this form. So where maybe there are two chunks of data, and taking the average out of these, if you're looking at some kind of a middle point among bunch of different data points. The problem that I would like to point out here is where the average point in the middle, it has we're sort of far away from a set of data. And also it is sort of far away from another set of data. So eventually this is the average, but it does not mean anything specific in terms of the individual data points. So maybe this is not really helpful for us to understand the data. So it really depends on how your data looks like. So maybe your data locally they are forming in one big chunk. But if that's the case, still taking the mean is useful. Or maybe it's not because your data is distributed in this way or in more messier way. So overall, we want to get better look of the data. So different set of techniques like clustering, like we are going to talk about today, and dimensionality reduction, where maybe you can come up with a low dimensional representation of your data. So if you can sort out this 5-dimensional data into 2-dimensional data, then we can draw them on the paper. So this kind of technique is called as dimensionality reduction. And overall, if you can visualize your data in some way, then that will help you understanding better as well. So exploratory data analysis sounds like something, but it is not really it does not mean really something specific. So overall, all of the technique that you can apply at the first stage in your data analysis is often called as exploratory data analysis. So this is just sort of background of our discussion. And let's move on to one of the specific technique that is clustering. So clustering is unsupervised learning. You want to find out innate groups from your data. So, still, this is unsupervised learning, so we don't have any class label or any indicator about the class membership. You have given a cloud of data points, and we want to make more sense of those clouds. So, say you have this kind of distribution. From here, we want to sort of find out grouping like this. This is just a quick example for your visualization. But there is two important principles while you are conducting clustering. So one is where you want to make sure the data points are similar to each other within a cluster. And between different clusters, where you want to decrease the similarity. So data points that fall in two different clusters, they should be dissimilar. So these are two important principles. So we talked about similarity, and speaking of similarity, we need more specific notion. So there are different similarity measures. So one is Euclidean distance. This is something we very well know. And cosine distance. So we talked about inner product and magnitude from the beginning, and the inner product over the magnitude could result in the cosine distance between two different data points. And Hamming distance, imagine you have two different binary sequences. So you have same number of binary digits, and you want to compare each digit one by one, and you want to count the difference between these two. So that is Hamming distance. Manhattan distance is, in other words, this is L1 distance. So these are sort of common distance metric, and there are a bunch more. So it really depends on what kind of data you want to analyze and what kind of data you're dealing with. So while you are working with the data in a long term, you want to study each of these distance metric one by one. So why we need the clustering then? The claim is made from here. So it should start from here. Clearly visible that if you have two-dimensional data, maybe you can find out some kind of a circle that in this group of this chunk of data, another chunk of data, and so on. Maybe you can do this by hand. Why do we need some kind of mathematical methodology? But that's the claim. Well, maybe you have too many data points, so you cannot group those jelly beans one by hand. That's a tedious task, and you don't want to do that if you have millions of those. Well, I don't want to do that. Well, that's one motivation. More important motivation is data are given in more than 3-dimensional, more than 4-dimensional data. And if that's the case, measuring the similarity between data points is difficult for us and it's not intuitive for us. So maybe we want to measure them in terms of some kind of metric using algorithm. So that's what the full purpose of machine learning is doing. So here is the initial motivation. And this initial motivation can be quantified by some kind of metric. And this metric can be optimized on my data set. So that's where machine learning algorithms play its role. Well, anyhow, imagine this kind of data where it was so simple. And let's move on to this kind of data. So data in 3-dimensional space. Well, still, maybe you can manually cluster them. Now, let's think about this data. This is basically 3-dimension plus colors. And eventually, this is 4-dimensional data, effectively. And clustering on this kind of distribution is where you may feel it's difficult. So there are different clustering algorithms. So one is a connectivity-based approach. And one representative example is hierarchical clustering. The other one is a centroid-based clustering algorithm, and the representative one is K-means algorithm. Distribution-based approach that is a third member or third category, and mixture of Gaussian is one representative example. And there is a graph theoretic one, and spectral clustering is the key member. Well, out of these, we are going to focus on these two because these are algorithmically sort of doable at the undergraduate level. And mixture of Gaussian, it has lots of good insight about the methodology and derivation. So maybe I will briefly mention this guy. But anyhow, in this slide deck, we are going to study these two methodologies.